All right, let's get started. Thanks for coming in today. I don't know if anybody will get home tonight, but if you don't, you could always just spend the night working on your assignment 0 or assignment 1. All right, so today we're going to continue talking about the operating system interface, and in particular, we're going to finish up fork. We'll answer this burning question, I'm sure, that has been keeping you guys up since Monday about why we added a level of indirection to the way that processes manage your files by talking about pipes and how pipes can be easily created after fork. And then, we'll get as far as we can into sort of the rest of the process-related system calls. So we'll talk about how processes change, how processes die, and then sort of what the communication that we can establish between processes beyond the grave. So just a couple of announcements today. So due to sort of shifting enrollment, we're down a TA. We lost Diablos, which is too bad. Happily, we have 3 fantastic TAs left, which is awesome. We started up office hours this week, as announced. Please come to office hours. We hold them. They're not for our benefit. We hold them so that you guys can come and get help on the assignments. From the activity on Piazza, I can tell that there's a lot of people that are getting started on assignment 0, which is awesome. But a lot of those questions and these little hurdles that people are running into will be resolved way more rapidly if you come to office hours rather than posting on the forums, right? We will do our best to monitor the forums and answer the questions as best we can, but frequently it's just going to be way more efficient for you guys to come to office hours, ask the same question, a TA will help you with it, and it'll take minutes instead of hours, okay? So please come to office hours. We do a lot of them. They're there to help you guys. And if you come now, you won't have to be in the line that will form, in the week before spring break and right at the end of the semester, right? So we've managed to get a room for the weekly recitation/help session, which is going to start today. So that's going to be in Talbert 107. Essentially, I think we're just going to run the recitation that we're running on Tuesdays and Thursdays. But I think it's a bigger room. I think it seats like 100. So it's a good chance for some of the graduate students who want to attend the recitation to come and see that material. And if we have multiple TAs available, we may be able to do some help sort of alongside, right? So we'll try that today and see how it goes. And then also, apologies for the problem yesterday with recitations. It turns out that was the physics department's issue with sort of trying to have 2 particles in the same place at the same time, right? Our particle has the permission to be there. Their particle needs to tunnel somewhere else. So we'll take care of that for next week. And also, so today it's a little nicer. Maybe somebody read the angry note that I posted through some random web form on the facilities website, which seems to be the only way to contact them. But I will try to keep the temperatures in here down to like a dull roar. Right? I mean, it's cold outside, so it would be nice to be warm in here. But last time, I could tell people were like, just starting to have a there's a word I'm trying to use. I don't know what it is, but it was starting to put people to sleep, and I don't want that to happen. So, all right. So last time we talked about file handles, and we started with file handles really as a way of getting ourselves to fork, and then we talked about fork, right? Any questions on Monday's material before we plunge onward? Any questions? Oh, yeah.
Could you go over the basic indirection again and what the importance is?
Yeah, so indirection, right? So I might actually have some review about this. Let me see. Yeah, OK. Can I go through the review, and then we'll come back to it? Should have asked for questions after the review. All right. So today, let's finish talking about fork, and we'll start on exec, right? So file handles, right? Remember, the file handles system, so the way the file handles are set up on Unix-like systems establishes 3 levels of indirection. There are 2 mappings I have to perform to get from what the process uses to manipulate files to what the operating system uses to represent files. So who can help me? Let's try to start at the top and sort of work our way downward. What do processes see locally after calls to open? You see a file descriptor. And what's a file descriptor? It's just a number, right? It's just an int, like 5, our favorite file descriptor, or 6, second best. Right, so the first level of indirection is mapping a file descriptor, which is what processes see, to a file handle, right? What's the next level of indirection? So I know I've got two of my levels. I've got file descriptors, file handles, and then what am I going to use? What am I going to map file handles down onto? Yeah. Yeah, like a file object, right, which is something that's maintained internally by the operating system, right? So remember, we also said that file descriptors are, tell me about how these objects are shared, right? File descriptors are what? So they could be private to the process, they could be shared sometimes, or they could be always shared, right? File descriptors, completely private, right? A file descriptor is mapped only at a specific process, right? What about file handles? They can be shared sometimes, right? With very limited semantics, and we're going to finish talking about those today. What about file objects? Always shared, right? In theory, sort of one file object on the system per open file that's in use by any process, right? So if two processes open the same file, they will have different file descriptors. Usually they will have different file handles, except in one particular case, and there will be one file object being maintained by the operating system. And the file objects actually allow the file system to find the blocks on disk that store the content of this file, assuming that it's stored on disk, right? So the file descriptor, again, is what processes receive from open. What is the file handle? What information is stored in the file handle? The offset. So what is the offset? Or let me ask you this. Well, how is the offset used? When is the offset used? Yeah. Yeah, so remember, read and write on Unix don't ask you to specify the start. They just ask you to specify how much, right? So when I make a call to read, I tell the operating system how much I want to read, but I don't tell it where to start, because it maintains that position for me. When the file is open, usually the file offset is initialized to 0, so the first read I do will return the first 512 bytes of the file, right? Okay, and then what about the file object? What other, what other information could be in the file object? I mean, I need it to locate the disk blocks, right? So, but it also has any other information about the file that's shared between multiple processes that are using the file, right? Okay, so now we've established this 3 levels of indirection, and we had this burning question, right? Which is, why are we going to do this? Have I answered your question yet? Okay, let me know. I might not have. I think I've told you what the indirect levels are, but why will we do this, right? So and remember, the idea here is to allow different parts, and this is sort of a nice system design principle, right? To allow different pieces of state to be shared with different semantics, right? So each process maintains and manipulates its own file table independently from every other process, right? So we talked about how the file table is copied during fork, but we also mentioned that the child process is free to then manipulate the file table in such a way to destroy all potential connection with its parent, right? So I'm a process, my file table is mine, right? Nobody else can change it. The file offset, because it's stored on this file handle, which is shared sometimes, can be a piece of shared state that can be shared between parents and children after a call to fork, right? And the file objects store information that's shared among all processes, and that's maintained by the operating system internally, right? All right, so I don't want to go through too much of this, right? So we talked about fork. Fork creates, well, let's do a little more review. Fork creates a process that is a what of the calling process. It's an identical copy with a couple of exceptions, right, which we talked about with respect to threads and potentially with respect to the fork interface, which might allow me to make more fine-grained copies of processes. But for the sake of this discussion, fork makes an identical copy of the process that called it, right? After fork, the process that called fork is the parent. The process that is created is the child, right? And they have a special relationship, right? At least briefly. Okay, so we did file handles, we did fork. Why is it up there again? Okay, so remember what happened is, because of how fork operated, after we copied all the other state, we ended up with a file table that had references to the file handles of the parent process, right? So fork went through, it copied one thread, remember, because potentially of issues with threading in fork. So I copy the thread that called fork. I copy the entire address space, and I copy the file table, right? So the child starts life with the same set of files open as the parent and sharing the file handles that are in use by the parent, right? And so I think this is all review. All right. And because of this, what this means is that if the parent and child start changing the offset in the file, those changes will be visible to the other process, right? So immediately after fork, if the parent does a read from the file, and then, so let's go through this, right? So let's say that I'm done with fork, and the child has not closed or reinitialized the file handles. And let's say that the parent process just opened this file. This is slides.html, and that file is using file descriptor 1 to refer to it, right? So let's say that the parent reads 512 bytes from the file. What will the file offset be when that read completes? It'll be 512, basically, 0 plus 512, right? Now, the child reads 512 bytes from the file. What 512 bytes from the file is the child going to read? It's going to read from 512 to 1024, right? In contrast, if the child had closed slides.html and then reopened it and did a read of 512 bytes, what 512 bytes would it read? The first 512 bytes, right? So again, this is the consequence of the sharing of these file handles after fork, right? All right, so, and remember the semantics of fork, right? So fork returns twice, which is weird. It returns 0 if I am the child, and it returns what if I'm the parent? It returns the child's process ID. Why does it do that? Well, but why would the parent want to know what its child's process ID is? Well, I'll keep track of it, but what? Yeah. So I definitely need a way to distinguish between the child and the parent, right? Because you'll see this kind of code a lot, right? Because usually after fork, I don't want the two processes to continue doing the same thing. I want the parent to do one thing and the child to do something else. But I'm still going back to the question, why would I return the child's process ID to the parent? It is to keep track of the child, but what specifically am I probably going to do with it? Yeah.
Oh, I was going to say, you can kill the process or call something.
Yeah, and how would I do these things? Like, maybe you could send a signal, but what else might I want? Who would I need to identify the process to? And who would like me to identify the process using this special number? The kernel, the operating system, right? So if I make a system call like wait, which we're going to talk about later, I need to identify the process to the kernel. Computers are good with numbers, not names. My child doesn't have a name anyway. It might still have my name, so it'd be weird, right? Who do I kill, me or my child? It's like some sort of like biblical dilemma. So here, I get the child's process ID back so that I can, refer to it later if I want to send it signals or communicate with it in some way, right? All right, so the real reason, how many people have, I think I asked this a couple classes ago, but how many people have run little, have created these little, they call them, I guess in Unix, one-liners, right? Which are strings of commands that are sort of separated by these pipe characters that do some sort of fancy thing, right? How many people have done this? I showed you some examples of these before, right? I took the output from PS, I piped it into grep to look for a particular string, right? And this is a very, very, very common programming paradigm on Unix-like systems, and this is how it works, right? So the preservation of the file handle after fork is extremely important to enabling this kind of behavior, right? But first I need to tell you about what's called a pipe, right? So a pipe is something that is what it sounds like, right? Pipes have two ends. They have an end where you can put something in, and then you have an end where you can read something out, right? Pipes look a lot like files, right? When you write to a pipe, what do you think happens? So when you write to a file, you potentially modify the contents on disk. When you read from a file, you potentially recover the contents that are stored on disk. What about pipes? What happens when I write to a pipe? Yeah. Well, but what happens to the other people who are using the pipe? Well, that's a case of using pipes, but.
Your child process could see that the file stuff's different and then read the changes in it.
Yeah, but just think about a pipe. These are all great examples of how pipes are used. When I write to one end of a pipe, what do I allow to happen at the other end? A read. Pretty simple, right? If I read, let's say I read from an empty pipe, what could potentially happen to my process? It might wait, right? So if I read an empty pipe, in certain cases, I might just wait until what happens? Somebody writes to the other end, right? So, pipes, again, are a communication. It's an IPC mechanism. They're built to sort of move data from one process to another, right? So when I run these little shell one-liners, what's happening internally is the second command is reading from a pipe, and the first command is writing to the other end of the pipe, right? So as PS begins to produce output, grep's reads begin to complete, right? And then grep is actually going to print to the screen, right? So I've got this nice, and these are sort of fun to play with. You can make little, so pipes usually create what's called an anonymous pipe object. Has anyone ever used a named pipe before? Even more Linux esoterica. Named pipes are cool. You should go play with them. So a named pipe actually allows you to create something that looks like a file and can be opened like a file. It has a file name, but it's actually a pipe, right? It has content that has length 0. Where are the contents of pipes stored, after they're written and before they're read? Usually stored in memory somewhere, right? It's not going to be stored on disk. Pipes aren't permanent. If the process crashes, the contents of the pipe are lost, probably, right? But yeah, so pipe contents are buffered in memory. I should not ask questions if the answer is on the slide, but it's good reading comprehension, questions. So, all right, so let's talk about this because this is pretty slick, right? So let me walk through the example of how we use pipes and fork to enable this really sort of classic Unix programming paradigm, right? So, and don't worry, I have a diagram for this because it's a little bit hard to wrap your mind around first, right? So let's say I want to use a pipe to communicate with my child, right? I'm going to run some program. I want to feed the output to my child, right? So before I call fork, I create a new pipe object by calling pipe, right? And it turns out when I initialize a pipe, I get access to sort of both ends of it, right? I get two file descriptors, right? One file descriptor refers to the end of the pipe, and the other refers to the beginning of the pipe, right? So I can write to one and read from the other. Okay? The next thing I'm going to do is call fork, right? I need somebody to talk to. I need a child to communicate with. And then after fork, me and my child carefully close one. So after fork, we both have those file descriptors referring to the same pipe object because we're sharing the file handle. Now I close my copy, and my child closes, I close the copy of the read end because I don't care about reading to the pipe. I'm going to write to the pipe, right? My child closes the write end because it's going to read data from me, right? Now I have this nice IPC mechanism that I've established that allows me to send information to my child, right? Without that information ever having to touch the disk, right? It's buffered in the kernel, okay? So here's code for how to do this, right? You'll see that, so this is an array. Remember that pipe returns two file descriptors. So these two file descriptors are stored in this array. Now I call fork, right? Now at this point, remember there are two separate processes running the same code. If the return code is 0, who am I? The child. And so I close which end of the pipe? The right end, right? Because I'm not going to write from the pipe. I'm going to consume data from the pipe. And then, now I can read from the pipe, right? Well, this read call, what will this read call potentially do until the parent has run? It will block, right? It's going to wait until the parent writes some data in the pipe, and then it'll read the data into this character buffer, and I can do something with it, right? So if I'm down here, who am I? I'm the parent, right? Which end of the pipe do I close? Read end, because I'm going to write data to the pipe. And now I can, write like a nice little message to my child. Right? All right, so diagram-wise, how does this look? Okay, I've initialized a pipe object. Again, remember I get access to both the write end and the read end. Now I call fork, and this is how this looks, right? My child has access to the same pipe, right? Now I need to detangle this mess that I've created, right? So I'm going to close the write end, and my child's going to close the read end, right? And now I have this nice in-memory buffer between processes, right? Questions about pipes? Guru. I think in practice probably no, because I think a lot of, the question is, does it matter which end I close, right? Could I close the other ends? I think pipe probably returns a bidirectional pipe now, so that I can actually send data both ways. But if it returned a unidirectional pipe, then it would be important which end I closed, right? But you can also conceive of a pipe object that works like a bidirectional pipe. So any data I write to one end is readable on the other end and vice versa, right? That's almost more like what you would think of as like a socket, right? Yeah, Natasha.
Do the children ever want to send messages to the parent?
Maybe. Yeah, it's possible. So if let's say I only have a unidirectional pipe, and I want to allow my child to communicate with me, what do I need to do? Two pipes, right? But I think Guru's right. I think in many cases I can get a bidirectional pipe, and that allows me to potentially consume data from the child using one pipe, right? So if I read from this end, right, I'll get data that was written in on the other end, right? So data travels one way through the pipe, not both. Yeah.
Why would you need to make another pipe? Couldn't you just keep the references that they had?
So if the pipe is unidirectional, right, then data only flows one way. So if I want data to flow the other way, right, I need two pipes, right? One that's going to communicate between me and my child, and the other one's going to communicate between my child and me. If I wanted only my child to communicate with me, then I could just close the other end of the pipe, right? And I would get a pipe that, instead of looking like this, looked like these with the arrows going backwards. Does that make sense?
Yeah, but I don't know. I'm just thinking if they could potentially use the same.
They could if the pipe allows me to send and receive data from both ends.
Do you have to close both ends? Or could you leave your prior arrows up there and then have the child write and the...
Right, so if I had a bidirectional pipe, then this is what I would do. I wouldn't close either end, right? And then if I wanted to communicate with the child, I have to write to this file descriptor, right? And if I want to receive a communication from the child, I have to read from this file descriptor, right? This gets a little weird on the slide, right? It'd probably be better if there were like two directions in the pipe to show that data could travel both ways. Good questions. Yeah.
So all whatever we write to the pipe is stored on the memory, right? So when we find registers to access.
Good question. So there are no bytes, there are no blocks on disk that are being harmed by this operation. So why use file descriptors? Why not make up, well, okay, never mind. I'm not going to answer my own question. Why use file descriptors? Yeah.
If you hold the information like the offset if you're reading from.
Yeah, the offset into a pipe isn't that meaningful, though. Right? Could be. Why not? Well, what's the I guess a better, maybe a leading question is, what's the alternative? Yeah. Yeah, I don't want, so what is a pipe? We talked about these maybe 2 classes ago. What is a pipe an example of? It's not a file, but it's accessed using the file interface. It's a file-like object, right? It supports the file interface, but it's not an actual file, right? And the reason we do this rather than having another interface is because then you would have another interface, right? One of the things that Unix has been able to do over the years is keep the interface to the kernel fairly compact, right? And one of the ways that we do that is by trying to reuse existing abstractions if they work well, right? So yeah, I could create a whole new interface to an object, or I could just say, hey, I mean, fundamentally, this object can be read and written to. It's got two ends. I can represent it as a file. It has some different properties that I might need to expose to the application, so it knows that this is a pipe as opposed to a file with blocks on disk. But mainly, the operations on this pipe I can support using the existing file API, right? That's a great question. All right, any other questions? Yeah?
Are there bidirectional pipes?
I think there are. Yeah, my knowledge of pipes is sort of trapped in the 70s, probably a little bit, but they're probably, why not? Bidirectional pipes. Yeah?
Just kind of curious, what's the importance of calling close on the MC pipes? Like, how does it gel?
I don't think you need to, actually. You can probably leave them open. As long, if it's a unidirectional pipe, I don't know what the semantics are of trying to read to the wrong end, right? It might fail, it might block, These are good questions. All right. I'll linger here. Yeah.
You have to clean up your pipe after you're done with the process, so that like handle.
Good. Yeah, so this is interesting. How many people have ever seen evidence of something that might happen here? So what could happen? I'm writing my really intricate one-liner. I've got 8 different processes lined up with all these like bizarro command line arguments, and my command line's like 3 or 4 lines long in my shell, and I'm feeling like a real power user. But what can happen along the way? I could have a typing error, and that could cause one of the processes I've configured to fail, right? And now the problem is I have this intricate pipeline that's been created, and the process fails. When the process fails, it's going to close that pipe, and actually you can sometimes see errors caused by the processes downstream. It's like pipe closed prematurely or something like that, right? So there was still data in the pipe, and I wasn't finished processing it because maybe it started generating some data and then failed, and then it closed the pipe prematurely, right? But yeah, if that happens, the contents of the pipe are lost, right? Because pipes are sort of these ephemeral things that I use to support a very specific and useful type of IPC. Right? Great questions. Anything else about pipes? Pipes are cool. Guru. Yeah. That's a great question. Yeah, I would have to think a little bit about the exact mechanics for doing this, right? Because clearly you need to call exec to, right? So someone needs to set up the pipeline, right? And my guess is you probably set up the pipeline first, and then you call exec so that each process is replaced by the image that you need to run, right? And then as we'll talk about, so Guru's getting ahead of us, right? So Guru is saying, how would you actually implement this in a real shell, right? And my answer is, I think the shell sets up the pipeline between processes first, and then uses a system call we're about to talk about, or maybe in about 5 minutes, to transform those processes into the commands that you want it to run. That's my guess. But I've never implemented this before. So, I write the G shell. Can multiple children read? I don't see why not. I don't see why that would be useful. Let's put it that way. One of the nice things about these simple pipelines is that the coordination between processes is quite simple, right? So, for example, if I'm writing like some sort of structured data to a pipe, right? My child can be sure that as long as I keep writing, it'll read data that makes sense to it, right? If I start having multiple children trying to consume the same pipe, what could happen is that one of them could get half of a structure and the other could get the other half, and it doesn't make sense to I, right? But I don't see conceptually why you couldn't have multiple children reading one pipe. Yeah. I don't know. Good question. Any other questions? I don't think so, though. My guess is that closing either end of a pipe is sort of a destructive operation, right? Or maybe closing the right end allows the read process to continue consuming from the pipe. But then the question is, how do I even reopen the pipe, right? The pipe that we talked about doesn't have a name, right? How would I open the same pipe? I don't have a reference to it anymore, right? Remember, I created a pipe by calling pipe, right? That created this completely anonymous object that doesn't have a name, right? If it's a named pipe, I could probably open it again. These are awesome questions. Pipes, awesomeness. All right, any other questions about pipes? Pipes. Going once, going twice.
You mentioned that you don't like having an import, but don't have the file descriptors for it?
Yeah, but once I close that file descriptor, right, that entry is cleared, right? And once I close the file descriptor, that number means nothing to the kernel anymore, right? The kernel is not an elephant. It forgets immediately, right? Like 4? No, I don't know anything about 4, right? You knew 30 seconds ago. No, it doesn't matter. Yeah, it's to prevent us from getting confused. There was another question back here. Yeah. I mean, let's put it this way. You can use pipes to create arbitrary networks of communication between an arbitrary collection of processes, right? Like a pipe allows me to set up a structured communication between a couple of processes. And especially with named pipes, right? If I use named pipes, right? So again, named pipes look like files. I don't even have to use fork to set up the pipes, right? I can start one process in one window and another process in another window that have no relationship to each other. And as long as they use the same named pipe, they can use the same abstraction, right? So yeah, there's literally nothing you cannot do without pipes. Or with what? There's nothing, I don't know what that sentence means, right? But there are a lot of things you can do with pipes, right? There are probably some things that you cannot do with pipes. And some things you cannot do without pipes. But. All right, good set of questions. Yeah.
Couldn't you just, like, instead of using pipes, actually like open up a file with a parent? And just have the
Yeah.
parent write and
Yeah. They never file. What a pain. And it's messy, you know. It's not in memory. It's on disk. And yeah, I mean, you know, again, I mean, you could do something like this from a file. What's the other difference with a file, though? Yeah. It might be slower, but also pipes are really more of a queue, right? Like when I read, I'm consuming from the pipe in the same order. When I'm writing, I'm sort of pushing data into the pipe, right? You can do that with a file, but it requires a little bit more gawkiness than you probably would want to do, right? You could try. You could probably implement it using files. A little bit of. No clue. Yeah, I don't know. I mean, it depends on so. Okay, so that's actually quite interesting, right? So let's say I have two processes that are sharing a pipe. What might the kernel try to do to avoid? So in what case would the contents of the pipe get really big? What's that? No, let's say both processes run. They're running normally. But in what case would data be building up in the pipe?
You're writing to it, but not reading from it.
Well, maybe the process maybe I'm sort of just writing information from a file to some really, really heavy-duty processing script that's slow, right? So it just might not consume the contents of the pipe very fast, but the producer might produce a lot into the pipe, so the pipe contents might start getting really, really big, right? What could the operating system do to prevent this from happening? Yeah. Yeah, and then once the max size is hit, what would happen? Yeah, so what I want to do fundamentally is I want to slow down the producer and give the consumer more time to run, right? And so what you could do is I could set a limit for the size of the pipe. Once that limit is reached, how do I block the producer? Well, but when do I have it wait? When it writes, right? So I can have a write to a pipe block if the pipe is full, right? What that means is now I give the consumer, right, the person who the process is reading from the pipe, a chance to catch up, right? Do some more processing, get stuff out of the pipe so that the size goes down, right? So if I'm intelligent about how I schedule things, I can certainly make sure that the size of pipes doesn't grow to consume all the memory on my system, right? This particular piece of functionality using pipes is a system call, right? So this is done in the kernel. What's that? Well, no. How do I implement the wait? When the consumer goes to write to the pipe, I just block it, right? So a lot of times writes will complete fairly quickly to a pipe because all I'm doing is moving data to memory. But once the pipe is full, the write could block for a long time, right? Until the consumer has consumed enough data that I allow the write to complete. So I don't need any special tricks, right? I just use the same pattern of accesses that the processes are used to. It just means that at some point I'm going to start favoring the consumer if the producer is really overwhelming the size of the pipe. Yeah, good question.
So is this waiting by the read of the write system call handled internally by them, or do we have to be wary of this?
Who's you? Are you the operating system in this sentence, or are you the process? in your, no, it's done completely internal, right? So you could have a little piece of code that's just writing to the pipe, right? And at some point, it's just going to stop, right? And the next time you get to run will be when the pipe's contents have gone down, right? So the process of making sure the pipe doesn't grow is handled by the operating system internally. Right? Processes don't have to do anything special.
Aware that they're writing to a pipe or
Yeah.
something beneath them.
Well, how, in this example I just used, how would I be aware that I was writing to a pipe? I used pipe to create the object, right? So, it's my own code, right? So I use the pipe system call. Now I have what I know is a pipe, right? But technically, write can block, right? I mean, a blocking write call can block for an indeterminate amount of time. That's part of the interface, right? So when and this is kind of an interesting thing for me to just emphasize. When you make a call to write, the operating system doesn't guarantee that that call is going to complete at any particular time, right? If it's on disk, maybe it completes really fast. It might be buffered in memory. It might complete really fast. It might be a pipe. It might complete immediately. It might be a network file system that's down, right? In which case, that write could block for like a long time, right? And some network file systems have special special ways to fail out of the write if that happens, right? So yeah, there's no semantics about the return to write. When you ask the operating system for help, the operating system can take, in certain cases, as long as it wants to take. Right? Yeah. What's that? Is pipe a circular? Well, a circular queue doesn't seem very useful because how do I get objects in or out of it, right? If it's a circle, so I'm not exactly sure what data structure you're referring to, but when I think circular queue, I think, how did those objects get in there, right? Yeah.
Is there a default size for the pipe, or can you change
Don't know. So these have been great questions, and I think we're getting to the point where I need the man page for pipe open in front of me, right? So that would be my suggestion. No, I don't mean to be dismissive, but I just don't know, right? I would go check it out. I'm sure there's a default size. It's probably a way to configure the maximum size of the pipe when you create the pipe object. But yeah, just go run man pipe, right? And you will get a lot more information written by someone who's a lot more authoritative than me about pipe, right? Maybe not about other things, but about pipe. All right. So I want to talk. Let's see how we're doing at time. Good. Okay. So I want to talk about fork, right? Because the split between fork and the next system call that we talk about is kind of interesting. And one of the things that's probably jumped out at you, or maybe it has, I hope it has, is that fork is a fairly intensive and sort of expensive operation, right? Let's say I have a process that has a huge address space that's all full of stuff, right? It's been running for a long time and it's using a lot of memory. It calls fork. Now the operating system has to create a complete copy of this, right? Which means that the operating system has to find a bunch of memory to copy it into and then copy the contents over, one block of memory at a time. And the thing that's frustrating about fork in particular from an operating system perspective is frequently what's the next thing that happens after I call fork? A lot of times I call fork because I actually want to run something different, right? That's something that's different than me, fundamentally, completely 100% different executable, different everything, right? So you can imagine fork being like, if you were buying a house and you went to your friend and you were like, you know what, I love your house, can you create a complete replica of your house in this new spot I've got? And he went and he spent all this time finding all the stuff that he had in his house and putting it in the exact same spot all over the place. And he was like, here's this great house. And you're like, OK, I'm going to change everything now. And you come in and you just throw out everything, repaint, fill the house with your own stuff. And he's like, why did I do all that work, right? Why didn't you just tell me you were going to do this? And so it turns out that I don't know what the percentages are, but I'm guessing that if you look at usage of fork on Unix-like systems, I don't want to guess, but I'm gonna say that a lot of the time, the next thing that happens is a call to the next system call that we're going to talk about, which is called exec. And exec completely transforms a process using a new binary, right? The problem with fork, of course, is if you only have fork, you can only create copies of the same process, right? And that wouldn't create a very interesting system, right? You'd have all these copies of init. How many people have heard of init before? Init is not a very interesting process, let's put it that way. Like, you would be very sad if your system could only make copies of init, right? Which is the first process that's created by hand when your system boots up, right? So we need a way for processes to change, but this also has to do with fork, because fork is just all this work, right? And so there are two ways around this problem that operating systems have pursued, right? So keep in mind, fork also does get called by processes that just want to create new clones of themselves. And there's valid reasons to do that, right? We talked about web servers that use fork to create lots of different copies to handle incoming connections, right? So I can't just completely replace fork with something like exec that also creates a copy, right? And so there's two routes here, right? One route is that we can optimize the existing semantics, right? Basically saying, I've noticed a pattern here, right? The pattern is that fork is frequently followed by exec. And there's a trick that I can play to avoid copying a lot of that memory, right? So that's one strategy. The second strategy is I could just change the semantics of the calls slightly, right? And so at the top, so the first option is through a technique called copy on write. I'm not going to describe copy on write right now, but we'll talk about it in a couple weeks when we talk about memory management, right? The copy on write is this really slick trick that the operating system can use to essentially avoid making copies of all that memory that I potentially needed to copy in order to fork the process, right? The other thing I can do is change the semantics, right? And so there's another system similar to fork that's called vfork, right? And vfork will essentially fail if the child does anything but immediately call exec, right? So what vfork, and the way that vfork does this, gets away with this, is it doesn't copy the address space, right? So if you try to modify the address space after vfork, you don't have one, and so you die, right? And so if you know that the reason you're calling fork is to immediately call exec and run a new executable, then you can call vfork instead. The way that the operating system gets away with not copying memory is by enforcing the semantics, causing you to fail if you try to modify the memory that you don't have, right? So this is these are kind of interesting, interesting sort of approaches that have been taken by Linux-like systems. The interesting thing here is that what Linux hasn't done is had kind of a new system call that both forks and execs, right? As far as I know. Right? And again, that's partly because of this design philosophy in Unix, which is to try to keep things as minimal as possible, particularly keeping the interface between the operating system and user applications and processes as lean as possible, right? All right. So I think I mentioned this before, but fork now has this. So now I'm just going to contradict what I just said, which is that we've added a different and much more flexible system call on modern Linux systems called clone. And clone sort of gives you this menu, right? Rather than saying, I'm going to copy everything, it says, do you want me to copy the address space? Do you want me to copy the signal handlers, for example? Do you want me to copy the file descriptor table? And sort of the calling process can make these fine-grained decisions about this, right? And the other thing that's cool about clone, I think, is that your cloned copy doesn't have to start running at the same point as you were, right? You can actually pass it a place for the child to start executing, right? So that almost starts to feel like creating a new thread, but that new thread is actually running in a new address space, potentially. So that's kind of cool. All right, so if you imagine over time, as I've called fork, and then again, we'll talk next time about exec, essentially on any system that you're running, there's this tree of process relationships that's formed, and there's this kind of neat utility you can use called PS tree. I don't know if this is installed on Timberlake. It'd be fun to run on Timberlake. It's probably huge. Because there's just a lot of people there, right? It's a big tree. But on your own little, virtual machine, which I hope we install this tool. If not, it's easy to do. And so this is an example. This is actually on the old class website. This shows me the output of PS tree. So this is kind of so here's init, right? Remember I said init is the root of the tree. It's the first process that's set up by the system. Because init has no 1, 2. Init has no fork, right? It's like which came first, init or fork, right? And of course, init came first because you can't call fork until you have a process. So here's init. And then a lot of other processes on the system that have been created are actually attached to init, right? And a lot of actually these were actually started by init, right? So for example, Apache 2. What's Apache 2? It's a web server, right? And here's the interesting thing. So what's all this stuff, do you guys think? Yeah, so here's a parent, and then, but what's this? Can you guys kind of guess what this notation is? How many children does this Apache process actually have? It has 5, right? It's got 1, 2, 3, 4, 5. What are these? Threads. Yeah. So remember I talked, I think last time, about how some servers use a mixture of fork and threading, right? So I get some multiprocessing, some multi-threading. We'll come back to reasons why you might want to do either multiprocessing or multi-threading. Clearly, one reason you would want to do multiprocessing is you can have access to more system resources. On the other hand, IPC is a little bit more complicated. Yeah, Tom? No, how many threads? So Apache has 2 copies. So this Apache parent has 2 children that each have 17 threads each. And then it has 2 other children that, for some reason, each have 26 threads each. I have no idea why Apache chose to set itself up this way. Right? But it looks like the total number of threads that Apache has is, let's see, 86. All right, so there are, is that right? I hope so, man. I wasn't fixing. Yeah, I think it's 86, right? Yeah. So there are 86 little Apache threads there waiting for your request, right? And they are split between 4 processes. Yeah, James.
Is there one for the one on top too?
You know, my guess is that this Apache is not actually servicing requests. It's probably some like slave driver that's trying to figure out how to get the other ones to work or something. I don't know. It's probably in charge. This is the boss Apache, right? And these are like the little worker ones. I actually don't know what they're doing, but my guess is because of the structure here, this one, particularly because it has no threads, right? You know, web servers want to have threads because threads allow them to separate requests, right? And then down here you can see all these other things that were also started by init, right? These are various system daemons. This is exim4 is a mail server. This is one of the tools that allows you guys to clone your Git repositories, et cetera, right? All right, final little bit of code for the afternoon.
Oh no.
So if you want to, I don't know, like I mean, someone should perform the experiment, right, and see what happens if you write and run this code on Timberlake or something. You can run it in your own VM, and it'll be fine. It'd be kind of fun to see what happens, right? But if you run it on a machine where there are other people on it, the reaction of university administrators to this sort of thing varies, right? But again, we'll never know what happens until some brave person tries it, right? In theory, they actually might have some mechanisms to prevent this from happening. But what does this do? Yeah, so this creates an exponential growth of processes, right? And so my favorite sort of image for that is, right? More. OK, so on Friday, we will talk about exec, and we'll probably get through the rest of the process-related system call interface. Help session today, 4 to 5. We've got office hours Thursday, Friday, and we'll see you on Friday.